Hello, probstats, and welcome to Chapter 5. We are on probability distribution, so you should have Chapter 5 out. You will need your calculator, and I don't think we'll need stat disk today, but we will find out. Okay, let's go. All right, Chapter 5, Section 1 is about probability distributions, and here we go. So when you go through this here, we're going to use random variables and probability distributions. We're going to talk about the distributions and what we have to have, the requirements, because that is important this time. We're going to calculate the mean and the standard deviation and decide if they're significantly high or low. So your two standard deviations above and below the mean. Okay, just vocabulary to make sure we know what's going on. A random variable, all right, a variable, it represented by x generally, it has a single numerical value determined by chance and for each outcome. A probability distribution gives a probability for each random variable. It's expressed usually in the format of a table, formula, or a graph. A discrete random variable has a finite or countable set of values, such as tossing a coin or whatever else we want to do. So now let's go on. We have to find the probability of a distribution. These requirements have to be met or we cannot use this procedure. Okay, first one, there's a numerical, not categorical random variable. Its number values are associated with corresponding probabilities. When you add all of the probabilities up, so these are all the probabilities, you will get 1. It has to equal 100%. All right, if we get 0.99 or 1.01, we accept those. We accept those because those are rounding errors, but we try not to make them. Every probability in the set is between 0 and 1. It cannot be below 0 or above 100%. If that does not count, it does not work. All right, here we go. We have got a coin toss. Now, when we're thinking about a coin toss, X is the number of heads when two coins are tossed, is what we're talking about here. So X represents my number of heads. My options are no heads, 1 head, or 2 heads when I flip my coin. So the probability, so when you think about this, we have, if you think of your sample space, we have 2 heads, heads, tails, tails, heads, tails, tails. So the option of getting 0 heads, there's one option. All right, so that's 1/4. My probability is 1/4. All right, now you fill in the rest. Pause and do that. So the probability of 1 head was here. So that's 2 out of 4, or 0.5%. And the probability of getting both heads is 1/4 again, 0.25. So when we go through here, and we know the probability of 0 or 2 are the same, because this is either 2 heads or 2 tails, so it should be identical. When you add this up, we get 1.0. So that satisfies that probability. They are all numerical, and each one of their individual probabilities is between 0 and 1. So when you look through here, we have satisfied all 3 of our requirements. It is numerical. It adds to 1. Everybody's probability is between 0 and 1. Is X discrete or continuous? So, can I count it or can I not? The answer is yes, I can count it because it's 1, 0, or 0, 1, or 2 odds. All right, so it is absolutely discrete. Finite or infinite? We know it's finite because it's 0, 1, or 2. It ends. It does not go on forever. Okay, probability histogram or bar chart. Okay, close to a relative histogram, but now the probabilities are on the side for my labels. So the probability of 0, 0.25, or 0.5. So 0 heads is 25%. 2 heads is 50%. No heads is 25%. We've done well. Or 2 heads, I'm sorry. Your histogram that you could get to draw. All right, job interviews. Let's look at this. Okay, pause and see if it works. Okay, does it describe a probability distribution? And the answer is no. All right, when you look at this, this is above 1. It can never be above 100. This is bad. So this is over 1. So this is not possible. So can I create a probability distribution? The answer is no, because it doesn't meet the criteria. So since it doesn't meet the criteria, we should not create a probability distribution. Could I create a histogram? Sure. But it would not be a probability histogram. All right. Also, these here are not numerical. All right. So since these are not numerical and this is over 1, it does not meet 2 of the 3 requirements. All right. Let's look at the next one. Color blindness. All right. So I want to see about color blindness in males. I have 5 males. And out of those 5 males, researchers have found out that none of them are colorblind is 0.65%, 1 is colorblind is 2.287, and so on. 0 or 5 are colorblind is like no possibility. So, does this meet our thing? Pause and try. First thing you should have done is add them up. So when we add them up, we get 0.991. All right, it's not quite 1, but remember there are rounding errors. So yes, this is close enough. So it meets that requirement. All right, are these numerical? The answer is yes. So these are numerical. So that checks that one. They add to 1, so that checks this one. Are all of them between 0 and 1? The answer is yes. No one's negative and no one's above 1. Check. So all 3 requirements are met. So is this a probability distribution? The answer is yes. So if it is a probability distribution, we have to create our histogram. So we do not have to match this because they are all met. So in your histogram, all right, I'm drawing on a screen, so this looks terrible. So we have on the side, the probability goes here. And we have to get all the way up to 65%. So let's go by tens. 10, 20, 30. All right, so the probability, and then we had 0, 1, 2, 3, 4, 5. So 0, 1, 2, 3, 4, and 5. And we had to put those in. So 0 was 65.9%. 1 was 0.287, so almost 30%. 2 was 0.05. So 0.05, not even 1%. So we are like way down here. That's probably even too high. 4 is 0.004, so really, really small. 4 is even smaller than this, and 5 is non-existent. I hope you did well on your histogram. All right, when we have to do histogram and its parameters, the way that we find the mean in a probability distribution is we add up all x times their probability. So this is my number times its probability. We find all of those values, and this means we add them up. Next, we take x minus, remember this here is the mean, which we just found above, squared, and take it times its probability. And then to find the standard deviation, we take the square root of that answer. So recognize that these two things are the same. All right, let's give this a shot. All right, expected value, when we talk about that, that is the same thing as a mean. It's just another word for it. So you have to remember that expected value means mean, which is what we just had on the other page. All right, rounding off rules, we go one more decimal, just like always. And here we go. So mean, variance, we're talking about our coin tosses. So we have 0 heads, 1 head, 2 heads, and our probability. So this is our coin toss from earlier. Now, so we multiply these two together. That's what we've done here to get our probability here. All right, so this means I add those up, all of these up, and this gives me my mean or my average. So my mean here is 1. It doesn't always have to add to 1. I know that's a little confusing, but be careful with that. So now, to find x minus mean squared, you take, okay, sorry about that. So now we have the mean of 1. So next we have to find our standard deviation. So in order to find the standard deviation, we take our number, so this is the x, minus our mean, which we just found down here, so it goes up here, square it, times our percentage, our probability, and we get those answers. Take those and add them up. Now remember, this is the variance. In order to find the standard deviation, we just take the square root of our variance, our square root of 0.5, and we get 0.707107, or 0.71. Okay, rounding. So we got mean, 1.0, pretty easy since there's only 2 exact decimals. Standard deviation was at even 0.5. Round our, variance, round our standard deviation to 1 decimal, and we get 0.7. Technically, you probably could have used 0.707 since it's one more than the other one. Okay, pause and try yours. You're doing the color blindness one, and let's see how you do. Okay, I hope you did well. I just did a little bit here. I multiplied them out. I found the mean for you. I showed you the general form for calculating your variance, and then this here just carries down. So these are the numbers you should have gotten, with a total of 37.3767. So your mean is 0.403, or your expected value. You have a standard deviation of 0.3767. Square root of that is 0.6138. So this means out of 5 colorblind men, the expected number is 0.43, so almost a half, with a standard deviation of 0.6. Okay, this means we would expect to find, so if we take, what you're doing here is 0.4 plus 0.6, which equals 1. So this is 1 standard deviation above the mean. That's hard to read. And you would also subtract. So we would take 0.4 minus 0.6, well, that equals a negative 0.2. We can't have negative 0.2 men, so we put that to 0. So we would expect to find 0 to 1 colorblind men out of our 5. I hope you did well. Okay, range rule of thumb. Again, 2 were significantly high or low if we're 2 standard deviations above or below the mean. Nothing has changed there. Let's use our coin toss. So we have a mean of 1. Our standard deviation is 0.7. So all we do is we take our 1 plus 2 times 0.7, and 2.4 would be 2 standard deviations above the mean. So 2 heads is not equal to or higher than 2.4. Therefore, it is not significantly high, which is what we were looking for. Use your colorblind data is having 5 colorblind men significantly high. Okay, pause and try that. You should have started with your mean, which is 0.403, sort of, plus 2 times your standard deviation, 0.6. If you just used 0.6, that would have been fine. You would have got 1.6306 or 1.6. So, is having 5 men significantly high? The answer is yes, because 5 is greater than 1.6. So it is significantly high. There we go. Now, remembering your things, significantly high. Okay, X is the number of successes, N is how many times you tried it. Probably if X is or more is successive is it if it's above 0.05. So we're back to our p-values. X is significantly high, so it's written like this. It's less than 0.05. Our chances of that happening by, the probability of it happening by chance. Significantly low, we do the exact same thing, and we're going to use 0.05 again. Remember, 0.05 does not have to be 0.05. It can be 0.1 or 0.01. We have talked about that a few times. So 95%, 90%, or 99%. Remember, 95% confident, 90% confident, or 99% confident is what those are talking about. Rare event, So assumption probability particular outcome is very small. Okay, occurs significantly less or significantly greater than what we expect. Okay, we conclude that the assumption is wrong, just like before, if it's not doing what we think. Okay, you assume that 1 in 2 men are colorblind. This is your assumption. So you're assuming like a 0.5 probability right here of colorblindness. You conduct your experiment and you find that the probability of colorblindness is actually 0.2. The difference between your assumption and reality is 0.3. So you took 0.5 minus the 0.2, you get 0.3. 0.3 is greater than 0.05. So since this is way larger than what we expected, your assumption is wrong. So it is not a 50-50 chance. Expected value to make decisions. Okay, you have $5 to place on a bet on the Golden Nut Casino in Las Vegas. You narrowed your choices to one of 2 bets. You're going to bet on 7 on the roulette wheel. I've talked about roulette wheels before, so we're getting better. And craps. Okay, I know nothing about this, but according to this, there's a pass line. So you bet $5 on the number 7. Remember, the probability of losing $5 is 37 out of 38 because there's 38 spaces on the wheel. And our net gain then would be 175 if we win, because they're going to give you 180 minus your $5 for your bet. Okay, find your expected value if you bet $5 on the number in a roulette wheel. That's what we want to do here. Pass line and craps. Okay, the probability of losing $5 is 251 to 495. The probability of a net gain is 244 to 495. I'm taking their word for it. $5 on the line, you are given $10 that includes your bet. So the net gain is $5. So if you will win $5 if you bet on this one. Not as much. All right, now let's start here. 2 bets, we have to decide which one's better. Common sense. Probably neither, but we'll see. The probability and payoffs for betting $5 on the number 7. So, probability of losing $5 is 37 out of 38. You multiply these together and we get negative $4.87 roughly. If I win, I get $175, but that's only 1 out of 38. So you multiply those together and we get 4.6. When I add those, so you're adding these two together, I am going to lose on average 26 cents per round. All right, your turn. Calculate craps. Okay, when you calculate it out, you took losing times your probability of losing, you got a negative 2.53. Winning, $5 times your probability of winning, which is 2.46. So you can expect to lose 7 cents. So which bet should you make? The answer should be neither, because either way you're losing money. But if you're going to bet, craps is better than the roulette wheel. All right, now you have homework. You need to find the mean, variance, standard deviation of the actual probabilities for each number from survey question number 1 of our sample data. So this is what should happen. This is what did happen. What can you conclude? Are we significantly high or low? And then I will give you a baby dice dice that has a baby dice inside. I'm going to expect you're going to create a betting scenario, and I chose like odd even numbers. You can choose something else if you clear it with me first. All right, good luck. I hope you do well.